We often think of Earth's magnetic shield as this perfect static force field, right? But what if it wasn't? What if it actually had a memory, remembering what the solar wind was doing just a few minutes ago? This isn't just some cool bit of trivia. We're talking about a delay that has huge consequences for all our tech up in space.
So, have you ever wondered why a multi-million-dollar satellite, supposedly safe and sound inside our planet's magnetic bubble, suddenly gets, bam, blasted by the solar wind? This isn't just some random glitch. It's a real mystery tied to the fundamental physics of space weather. And today, we're going to dig into the research that's finally starting to crack this cosmic case.
All right, so here's our game plan. We'll start with the shield itself, then dive into the cosmic pressure battle that shapes it. We're going to uncover a big flaw in our old forecasts, check out the simulation that revealed a really surprising delay, and then, at the end, we'll talk about what this all means for rethinking space weather. Sound good? Let's go. Okay, first up, Earth's unpredictable shield. The big takeaway here is that our planet's first line of defense is not some static, rigid wall, not at all. And knowing exactly where that boundary is from one moment to the next is absolutely critical. I mean, think about it. If you're a satellite operator, you need to know if your expensive piece of hardware is about to drift outside the safety of the magnetosphere. Some satellites even use the magnetic field to steer themselves. So if that shield isn't where your model says it is, well, you've got a pretty serious problem on your hands.
So to really get why the shield moves around so much, we have to look at this epic cosmic tug-of-war that's happening 24/7. It really all comes down to a battle of pressures.
Okay, so the first player in this battle is the magnetosphere. The easiest way to think about it is just as a protective bubble around Earth, totally dominated by our planet's magnetic field. As long as you're inside this bubble, you're pretty well shielded from all that nasty solar radiation.
And the very, very edge of that bubble, that's what we call the magnetopause. You can think of it as the front line, the exact spot where the outward push of Earth's magnetic field slams into the inward push of the solar wind.
This slide really nails the whole concept. On one side, you've got the solar wind, this non-stop stream of charged particles blasting out from the sun, trying to squash our shield. And on the other side, you have Earth's own magnetic pressure pushing back, resisting it. The magnetopause is simply that point of equilibrium where those two forces balance out. But, and this is a big but, here's where things get tricky. The models we've been using for years to predict where that balance point is, well, they have a pretty major flaw. They've been built on a simplifying assumption that just doesn't really match reality. See, the old assumption was that the solar wind is basically a steady, constant stream. You just plug in the current pressure and your model spits out the shield's location. Easy, right? The problem is, reality is way messier. The solar wind is actually incredibly gusty and chaotic. It's got its own magnetic field that's flipping and waving all over the place. It's way more like a turbulent river than a calm, smooth canal. So how in the world do you test this? It's not like you can just go out there and tweak the actual sun. Well, the researchers behind this study did the next best thing. They built a digital Earth. They used this incredibly powerful simulation to see what happens when you hit our magnetic shield with a much more realistic, fluctuating solar wind. And here's how they pulled it off. First, they fired up a well-known simulation, the LFM model. They started with a baseline test, hitting their digital Earth with a steady solar wind, just to see where the shield would be according to the old rules. Then they ran the real experiment. They introduced these wave-like fluctuations into the solar wind, just like we see in real life. And after that, they just sat back and measured exactly how the digital shield reacted. And what they found was kind of mind-blowing. The shield doesn't just instantly snap to a new position when the solar wind changes. No, it lags behind. It sort of remembers what the wind was doing just a few moments before. Okay, check this out. This was the first huge surprise. Now, you'd think that a gusty, fluctuating wind would, on average, push the shield in, right? Compress it. But the simulation showed the complete opposite. On average, the magnetopause was actually further away from Earth. The whole shield was kind of puffed up, more inflated than the old models predicted. And this is the killer detail right here. The simulation found an average time lag of about 10 minutes. Let that sink in. When the conditions in the solar wind change, it takes a full 10 minutes for our planet's magnetic shield to fully adjust. It's not instantaneous. It's a slow,
delayed reaction. This quote from the paper just sums it up perfectly. The actual instantaneous position of our shield can be significantly different from what the steady-state models would have you believe. And significantly different isn't just a few miles. We're talking up to one entire Earth radius. That's almost 4,000 miles of error. Okay, so this all leads to the final and maybe most important question. What does this actually mean for us? How does a 10-minute delay way out in space affect our lives? And, more importantly, all the stuff we have in orbit? All right, here's the bottom line. That time lag means our shield's boundary can be thousands of miles away from where our models predict it is. This makes our current forecasts way less reliable, especially during those gusty solar wind events. And that translates directly to a huge risk for satellites. A mission planner could look at their data and think their multi-million-dollar satellite is safely tucked inside the magnetosphere, but because of this delay, it's actually outside, completely exposed to damaging solar radiation. This research is a massive wake-up call. It shows us we need to build new forecasts that finally account for the shield's memory. So we'll leave you with this thought. We've just found out that our planet's own defense system has a memory, a lag time based on its recent history. It's just a powerful reminder that the universe isn't some simple, predictable machine. And it really makes you wonder, right? If our own shield is this complex, what other cosmic systems out there have these hidden delays and memories that we haven't even begun to discover?